Lee's class, and my name is Chen Yanli.
My name is Xun Xuan.
And today our topic is special temporal evolution of non-axis symmetry vortex rings. So first, what is vortex ring? Actually, the vortex ring is very common in our daily life, and it can be generated in the air or under the water. And the question is how to generate the vortex ring. So let's see the video first. So after the water is extruded from the tube, and due to the non-slip boundary condition, which means that the fluid velocity equals the wall velocity at a solid boundary. And also due to the viscosity, that the momentum can transfer from the center to the wall, and it will form the velocity gradient and ultimately generate the vortex ring. And in the video, we can see that there is a swirling structure like this, and this is called a vortex, which is the rotating motion of fluid around a common center line or point. And this is the flow field around the vortex ring. And there is a physical quantity called the vorticity, which is the curl of the velocity field to discuss this flow field. And the local maximum of vorticity is called the vortex core. And if we connect all the vortex core together, we can get the vortex filament. And the question is, what is the physical origin of the propagating vortex ring? So here is the flow field around the vortex ring, and let us reduce the flow field to this symbol. And as we know that the lower core sits in the flow field of the upper one, and also the upper core sits in the flow field of the lower one. So it will generate the self-induced velocity and make the vortex ring propagate forward. And this is previous work. People mainly use the circular vortex ring to do the head-on collision or to explore the transition to turbulence. And the rings they use are axisymmetry rings, which means that its vorticity is uniform along the vortex filament. And our question is, how about we generate a non-uniform vorticity distribution vortex ring?
Okay, now let's talk about our goals. And first of our goals is the generation of symmetry breaking vortex ring. And the second goal is the spatial temporal dynamics of non-axis symmetry vortex ring. And so as we can see, there's two groups of the tubes. And for the first one, which is this, we call it's the axis symmetry is the normal tube, and the other one is the non-axis symmetry tube. And here is the experiment setup that we used, and we used the DC motor with piston to inject the vortex ring, and we also have the computer control motor system to control the stroke and the vortex ring. So here is our control group, which shows the axis symmetry group, and as we can see that here is a normal vortex ring and with a circular core, and it propagates with a straight direction. Okay, so how do we track the flow field? So here we use particle image velocimetry, which is PIV, and we use the laser sheet and the tracer to visualize the flow field. And here is the consequence of the result of the core vorticity evolution. Here the vorticity is calculated by the curl of U, and the vortex core is the local maximum of the vorticity magnitude. And as we can see that the circular one is stable, the shape of it is stable, and the core vorticity remains constant. And what about the non-axis symmetry vortex ring? So here let us introduce more detail in this case. And here we see the inclined cut circular tube. We call it n=1, which is mode 1, and the second one is the draw inclined cut circular tube, which is n=2, mode 2, and which is look like this in the real, and we made them by laser cutting. Okay, so now let's go to the mode 1 case, and here's the demonstration video. Okay, what did you see? And so you might have noticed that the vortex is actually generated at a short edge first, then With in the progress, the vortex ring slightly tilts in the propagating direction and ultimately becomes straight. And let's replay the video again. Okay, so if we draw the evolution of the core vorticity, then we will notice that here the blue line is for the upper core and the red line is for the lower core. And we see that the upper core and the lower core vorticities oscillate with a clear phase difference. And if we take a closer look at the beginning, then we will actually see that this progress, the whole evolution that corresponds to the video here, picture here. And we see that there are actually clear vorticity different in the upper core and the lower core. So why does the core vorticity exchange? And how does the propagating direction change? So now let's get more details in the beginning. And here we see that upper core is generated first, and then the upper core dissipates earlier than the lower core. And the lower core vorticity is stronger than the upper core. So which makes that the upper core sits in the lower core's field, and the intensity of the inner field, which is this line, is stronger than the outer field, and which will generate a velocity gradient and also make the vorticity transport from the lower core to the upper core. And how does the propagating direction become straight? So here, let's talk about the whole progress. So here we see that the short edge generates the upper vortex first, then the vorticity of the upper vortex dissipates, and the vorticity of the upper one becomes smaller. And the upper one moves faster due to the induced velocity, and the ring tilt, and this progress will keep going with the vorticity transfer from the lower one to the upper one, and the vorticity of the lower one becomes smaller, and this progress will keep going until the vortex decays and the propagating direction will become straight ultimately. And how about the n equals 2 case?
So also let's see the video first. And what do you see? So in this video, we can obviously see that the core shape just changed periodically. And then let's watch the video again. And here we also calculate the core vorticity, and we can obviously see that the upper and the lower vortex core vorticity varies in phase. And let's take a close look. So at first, the shape of the core is circular, and as the vorticity decreases, then the core shape becomes elliptical, and it ultimately changes back to the circular again. So here, the vorticity of the both cores just varies from high to low simultaneously with the change of the core shapes. And here's the 3D vortex ring conceptual demonstration, and this is how the M2 vortex ring oscillate in real space, like this. So, and the physical principle behind it is very similar to the case of mode 1, and it's due to the non-uniform vorticity distribution along the vortex filament. So, it cause the exchange of the core vorticity and make the vortex filament stretch. And if we see the cross section, then we can see the deformation of the core shapes. And here's our summary. So in the case of the m equals 1, then we see that the core vorticity just exchange periodically, and also the vortex ring just slightly tilts in its propagating direction. And in the case of m equals 2, we notice that the vorticity just varies with the change of the core shapes.
Okay, but the story didn't end yet. So you might notice that we actually have another tooth at the bottom, which is in this vertical direction. Then you might ask, what is this for? So this one is for. We also did the other experiment is about the collision of vortex ring on different angle, which is 90 degrees in this case. And as we can see that here, we see the exchange of filament in the collision, and it ultimately form a 45 degrees angle. And here, this is our end of this talk. So thanks for listening.